Hi students, in this PPT I am going to explain question number 3 which is given in the handwritten note. So question number 3 deals with the design of braced slender column. So as we discussed in the first PPT, braced column is a frame which is having lateral bracings or wall to provide lateral stability. Okay, so this column will not be subjected to sway or lateral drift. So this is in this figure, this is the bracings provided, and this typical frame is termed as braced frame. Once the braced frame is subjected to lateral load, it may undergo curvature or bending like this. So two types of curvature is possible, single curvature and double curvature. This is very important. After moving to the question, you will understand more about its importance. So once the braced column is subjected to lateral load, it may undergo either single curvature or double curvature. So this profile shows the single curvature and this shows the double curvature. So moving on to the question, our question is, a braced column 300 mm by 400 mm is to carry a factored axial load of 1200 kN and factored moment of 50 kN and 30 kN with respect to the major axis and minor axis respectively at the top end. The column is bent in double curvature in both the direction with the moment at the bottom end equal to 40% of the corresponding moment at the top. Design the longitudinal reinforcement for the column if its unsupported length is 7.2 meter with an effective length ratio of 0.85 in both the direction. Use M20 concrete and Fe415 steel and provide 60 mm effective cover. So in this question it is mentioned the column we need to design is a braced column. Okay, the first two questions were dealing with the design of an unbraced column, and this particular one is showing how to design a braced column. Okay, so this is a braced column and its dimension is given 300 mm by 400 mm. So it is a rectangular section with B equal to 300 mm and D equal to 400 mm. And this particular column is carrying a factored axial load of 1200 kilonewton. So Pu is equal to 1200 kilonewton and factored moment of 50 kilonewton meter and 30 kilonewton meter with respect to the major axis and minor axis. And also both the moment is acting at the top end. Okay, so as I discussed in the previous PPT, our major axis is usually x-x axis and minor axis is y-y axis. So in this particular question, it is given at the top end of the column. So in this figure, I am showing the this is a representation of a column. So let this 2 represents the top end and 1 represents the bottom end. Okay, so in the question it is given at the top end, that is this 2 represents the top end. So at the top end the moment about x-axis is 50 kilonewton meter, that is major axis, x-axis is 50 kilonewton meter, and about y-axis, that is a minor axis, is 30 kilonewton meter. So both the moment given in this question is at the top end. And the column is bent in double curvature. So this is the indication of double curvature. Okay, so this particular question is, this column is subjected to double curvature. It is having importance. I will explain it later in the design. So it is having a double curvature in both the direction with the moment at the bottom end equal to 40% of the corresponding moment at the top. So we know at the top end mx is 50 and my is 30. Correspondingly at the bottom end or at one end, this end, at the bottom end, the corresponding moment will be 40% of that available at the top end. That is given in the question. And it is asked to design the longitudinal reinforcement for the column if its unsupported length is 7.2 meters. So unsupported length is usually notated as L. So L is given as 7.2 meters with an effective length ratio of 0.85 in both the direction. Usually the effective length is calculated based on the support condition. Here it is directly given. We need to take the effective length as 0.85 L. Okay, in both direction means in x direction and y direction, the effective length is taken as 0.85 L, 0.85 times 7.2. And the materials used are M20 concrete and Fe415 steel, and the effective cover provided is 60, that is small d dash is given as 60 mm. Okay, so moving on to the design, our first step is given data. So the unsupported length L is given as 7.2 meters, PU is given as 1200 kilonewton. Our top end is notated as 2 and bottom end of the column is notated as 1. Correspondingly, the moment in x direction at the top is 50. So it is notated as M2x. And the moment that in y direction or moment about y axis at the top end is 30 kilonewton, which is notated as M2y. Correspondingly, M1x is the moment at the bottom end about x axis is only 40% of this 50. Okay, so which is equal to 20. And M1y is the moment in bottom end about y axis is only 40% of this 30 kilonewton meter, which is equal to 12 kilonewton meter. So these are the given data. And our next step is computation of slenderness ratio, E minimum and Mu minimum. First, we need to check the slenderness in both x-axis and y-axis. Since it is a rectangular section, we need to check the slenderness ratio in both in x-axis and y-axis. Next, we need to calculate minimum eccentricity, and next we will calculate the minimum moment due to that eccentricity. So as we discussed in the first PPT, while designing a slender column, we need to calculate or we need to consider both initial moment or internal moment and additional moment. So in the second step, we will be calculating the initial moment. Okay. So first, Lx and Ly is given as 7.2 meters, which is the unsupported length. Next, we are calculating the L effective. That is L effective in x and y direction. In the question it is given, we are taking the effective length ratio is taken as 0.85. So Lex and Ley is taken as 0.85 times 7.2, which is equal to 6.12. And by calculating the slenderness ratio Lex by D and Ley by B, we have obtained it as 15.3 and 20.4 respectively. So both the slenderness values are obtained greater than 12. So the column is slender for bending about both the axes. Both axis means about x axis and about y axis. The column is acting as slender. Next, we are going to calculate eccentricity in both x and y direction. The equation for eccentricity is about x axis. Ex minimum is L by 500 plus D by 30, which is obtained as 27.73 mm, which is greater than 20 mm. And Ey minimum is equal to L by 500 plus B by 30. As I explained earlier, this dimension is the dimension which is perpendicular to the y-axis. And here this dimension is the dimension which is perpendicular to x-axis. So the equation for Ey minimum is L by 500 plus B by 30, which is obtained as 24.4 mm, which is also greater than 20 mm. If any of the value of the if any of this Ex minimum or Ey minimum is obtained as 20 less than 20, we need to consider at least at 20 mm. And corresponding to this Ex minimum and Ey minimum, we will be obtaining Mux minimum and Muy minimum, which is respectively 33.276 kilonewton meter and 29.28 kilonewton meter. So this is the internal moment due to the eccentricity. And since it is subjected to so next is computation of initial moment. So since it is a braced column, you need to consider a close which is given in IS 456. So as per IS 456 2000, close 39.7.1 knots of this particular close, page number 72. This is the particular close mentioned in the IS 456. And according to this close, our primary moment in x and y direction. The column is raised and bent in double curvature, hence M1x and M1y are negative. So here, by considering this close, we will arrive at the equation, the primary moment in x direction, MUX is equal to 0.6 M2x minus 0.4 M1x, where 2 represents the end having larger end moment, M2 represents larger end moment, and M1 represents smaller end moment. And thus minus is taken since it is having a double curvature. Okay, so finally the equation becomes MUX equal to 0.6 M2x minus 0.4 M1x, and which is obtained as 22. And also in this clause it is mentioned this MUX should not be more than 0.4 M2x, which is equal to 20. So that is a check, and this check is satisfactory in our case. And correspondingly MUY is equal to 0.6 M2Y minus 0.4 M1Y, which is obtained as 13.2, which is also should be greater than 0.4 M2Y, which is equal to 12. And this in both MUX and MUY is satisfying this check. Okay, and the initial moment in x direction should be taken as greater of MUX and MUX minimum. Similarly, the initial moment in y direction should be taken as greater of MUY and MUY minimum. So in the previous two steps, we have calculated MUX minimum, MUY minimum, and MUX and MUY. Okay, so by comparing these four values, okay, we are going to compare MUX minimum and MUX. Whichever is the higher value we'll consider for the further design procedure. Similarly, whichever is the higher value of MUY minimum and MUY, that higher value will be considered for the further design procedure. So by comparing these two values, this set of value MUX minimum and MUY minimum is obtained higher. So this is considered as the initial moment. Okay, so that's MUIX, initial moment in x direction is taken as 33.276 and MUIY is taken as 29.28.